Hi there. Today we'll look at ImageNet classification with deep convolutional neural networks by Alex Krzyzewski, Ilya Sutskever, and Jeffrey E. Hinton. So this paper is another one in the installment of our historical paper overview, where we go through kind of old papers that were or weren't very impactful and see what people knew at the time already, how this developed, and so on. Of course, this paper here, also known as AlexNet, was the one that started the deep learning revolution, so to say, or at least contributed in large part to it. It was the first paper that showed that you could train these very deep neural networks, and very deep in here is a relative term, but the first one that showed that you could actually use CUDA GPUs to train those large networks efficiently, and it won the ImageNet competition that year, and it did so by a very, very large margin. So kind of shook the world because previously computer vision was still doing like hand-engineered features and then using some kind of classifiers on top of those. This paper basically changed everything. So we'll go through the paper and we'll see what was already known, and especially I always enjoy with these papers, how did the choices that people make back then, how did they pull through to today? Sort of what arbitrary choices that Alex Krzyzewski made right here are we still doing today, and what have we learned since then? So the paper is written relatively straightforward, I have to say. It's a good read if you want to read it, and, you know, straightforward, and sort of gives you a little bit of an intuition of how much work must have gone into this, which is, I guess, a lot. And yeah, so they start off by saying that current approaches to object recognition make essential use of machine learning methods. This was also new, right? Object recognition wasn't always learned. Object recognizers, you could even do it in different way, like matching templates and so on. Machine learning was still one of the methods used, and of course today it's the method used. To improve their performance, we can collect larger data sets, learn more powerful models, and use better techniques for preventing overfitting. Until recently, datasets of labeled images were relatively small, on the orders of tens of thousands of images. Okay, so this especially at NORB, or here the CFAR10 or CFAR100, these are relatively small datasets with relatively small images as well. Like CFAR10 is 32 by 32 pixels. So they're saying that, okay, in these small data sets, you can solve it with classical computer vision models, but if you have larger data sets, and especially more realistic data sets, like bigger resolution and so on, you need bigger models. So they say, but objects in realistic settings exhibit considerable variability. To learn to recognize them, it is necessary to use much larger training sets. Okay, so they say that this ImageNet dataset is one of those larger datasets, consists of 15 million labeled high-resolution images in over 22,000 categories. And people keep forgetting this, and I am included in that group of people, that the ImageNet dataset is actually much larger than we know, when we talk of ImageNet. When we speak of ImageNet, we think of the ImageNet that has 1,000 classes and about 1 or 1.5 million images. However, that's only a subset of the much, much larger ImageNet dataset in many, many more categories. It's just that the ImageNet competitions were performed on this subset because I guess people thought, well, 1,000 classes and 1 million images is already plenty, so we'll do that. So that's, I guess, how that came to be. So their argument is right here. To learn about thousands of objects from millions of images, we need a model with a large learning capacity. However, the immense complexity of object recognition task means that this problem cannot be specified even by a dataset as large as ImageNet. So our model should also have lots of prior knowledge to compensate for all the data we don't have. So their main argument for using neural networks is that the size of the data set is so large, therefore we need a large model. Granted, they already recognize the the inherent connection between large models and a lot of complex data. But in the opposite, they say, well, even if we have that much data, the task we are trying to solve, object recognition, is way more complicated than the amount of data we have. So our model should also have lots of prior knowledge to compensate for all the data we don't have. Remember, at this time, convolutional neural networks weren't really, known to do anything. I guess they were used for handwritten digit recognition and so on, and were kind of on par with other methods. However, it wasn't like obviously clear that you would use them for image recognition. So here they have to make like a argument to convince people that, okay, we can use neural networks for these tasks because they have such a high capacity. However, neural networks, feed-forward neural networks, are already too powerful. They don't know anything about the data. Everything's connected to everything. And they argue right here, our model should have lots of prior knowledge to compensate for all the data we don't have. So they allude to the convolutional neural networks constitute one such class of models. Their capacity can be controlled by varying the depth and breadth, and they also make strong and mostly correct assumptions about the nature of images, namely stationarity of statistics and locality of pixel dependencies. So their argument here is that the convolutional operation is such a strong prior that is mostly consistent with what we know about images, that they are very well suited to computer vision. Again, something that was not abundantly clear at the time as it is right now. It's interesting to see how they get to this point where they say we need lots of capacity, but we also need a model with lots of prior knowledge. And of course, CNNs fit that very well. So they go into the problems of CNN. Despite the attractive qualities and despite the relative efficiency of their local architecture, they are prohibitively expensive to apply in large-scale, high-resolution images. Luckily, current GPUs paired with a highly optimized implementation of 2D convolution are powerful enough to facilitate the training of interestingly large CNNs, and recent datasets such as ImageNet contain enough labeled examples to train such model without severe overfitting. Again, so overfitting was also still like very much at the forefront of people's minds back then. Right now, we don't really care about overfitting that much anymore. Basically, we figured out that if we just build large enough models, we don't overfit, which is strange in itself, like this double descent phenomenon and so on. But overfitting was still a very much at the forefront of people's minds, and they do a lot of things here to prevent overfitting, which gives them kind of a boost in the test accuracy, which might actually not have been the overfitting that they're combating. So they do, for example, data augmentation already in this paper, and they always allude to, this is to prevent overfitting. However, we know nowadays that it might not be the overfitting that's combated in the by data augmentation. It might actually be have something to do with like regularizing your function, making it more smooth and so on. So you just see how coming from a classical machine learning perspective, overfitting was like the number one or one of the number one problems in classical machine learning, in SVMs and things like this. So it's safe to say that they thought if we built these large models, we're going to have a huge overfitting problem. And yeah, so that's why this pulls through right here. Also, one of the main contributions of this paper is to combine this CNN training with GPUs. Also, not very non-clear at the time. Like, it was known that you could do computation on GPUs, but the fact that these are, very capable for training the CNNs or generally neural networks wasn't something that was, known at the time. So this paper basically showed that if you use a GPU, you can get that much faster, and that makes it possible to train these big neural networks. Again, right here, the size of our network made overfitting a significant problem, even with 1.2 million labeled training examples. So we use several effective techniques for preventing overfitting, and we'll look at those. And the end, they say, the network's size is limited mainly by the amount of memory available on current GPUs and by the amount of training time that we're willing to tolerate. Our network takes between 5 and 6 days to train on 2 GTX 580 GPUs. All of our experiments suggest that our results can be improved by simply waiting for faster GPUs and bigger data sets to become available. And I mean, that proved to be absolutely true. We don't necessarily have bigger data sets right now, though we do, but certainly with faster GPUs and bigger GPUs, these networks became better simply by increasing their depth. And as you know, then ResNets came along, increasing the depth by an order of magnitude, and that gave another boost to computer vision. All right, so they talk about the ImageNet dataset here, and the main point in the ImageNet dataset right here is the fact that the images are plenty. So there are over 1 million training images in this subset with 1,000 classes, which was, a very big, that was on, like CFAR 10 had 10 classes, CFAR 100 had 100 classes. That was already a lot. 1,000 classes, that is unheard of before this data set. I guess not unheard of, but and 1 million training images. Completely crazy. And also, not only was it a lot of images, resolution was really big. So in the order of 256 by 256, whereas previous methods all were like 32 by 32. So definitely challenging data set. Even today, it's a challenging data set. All right, so the architecture. And there's this famous graphic right here of the AlexNet architecture. So briefly, they describe these convolutional layers right here. As you can see, there's max pooling already here. They have dense layers at the end. They do generally increase the number of feature maps right here while decreasing the resolution with max pooling. So all of this has sort of, kept until today. I guess they also took it from earlier work on convolutional neural networks that generally found this to be a good idea. And the important part here that is kind of special to AlexNet is you can see there are these 2 different pipelines. And, Alex, for cutting off this part right here, I mean, you just know, like, there's 8 pages. We need to, we have 3 lines too much. How can we fit the 3 lines? We've already cropped everything. Let's just cut off the top half here. It's essentially the same as the bottom. So space constraints in PDFs for conference submissions, ruining yet another paper. All right, but you can see there's this 2-column architecture right here. So this network was so large that it didn't fit on 1 GPU, so they had to split it onto 2 GPUs with the occasional intercommunication, right? You can see here there's intercommunication between the 2 GPUs. And there is also no intercommunication right here on this layer. This was very intricate. That was one thing that really didn't hold until today, I guess until now with things like, I don't know, G-Shard or so, where you have different weights on different GPUs again. I guess the invention of bigger GPUs made that sort of superfluous, but just imagine the amount of code they had to write. There was no TensorFlow at this point. I don't think there was even Caffe around. There was just CUDA. And just this cross GPU memory writing. I just imagine this to be so ugly, and big respect for writing all of this code. All right, so they go through a number of important things, and most of the things here aren't their invention, let's say, but they cleverly combine things that were already known about neural networks and things that were maybe developed somewhere that they have found to work really well. So the first one is the ReLU Nonlinearity. Now, of course, ReLUs nowadays are like abundant. Everyone uses ReLU's nonlinearities, but at that time, it was still very much in fashion to use something like the sigmoid right here, or the hyperbolic tangent. And why is that? Because the neural networks were still kind of inspired by the neurons, where you had the soma of the neuron and then the input dendrites with the input axons, and then you would sum up all the incoming signals, and then that would go over. So in a true neuron, you have this this kind of curve where if the input rises above this border right here, the action potential, maybe, I don't know what the English term is, then if it rises above that, then the neuron would start to spike, right? And if it's below that, it wouldn't. So people wanted to approximate this using some sort of a kind of differentiable, but something that's very similar to this step function. And that ultimately led to something like a sigmoid or a hyperbolic tangent. So people trying to stay close to biological neurons did this, but that gives you the problem that in this region and in this region right here, you have almost no gradient to learn from. So you can see that they argue that in terms of training time with gradient descent, these saturating nonlinearities, so the hyperbolic tangent and the sigmoid, are much slower than the non-saturating nonlinearity, this one. Following Nair and Hinton, we refer to neurons with this nonlinearity as rectified linear units. So taken from this, this other paper, they say, okay, we use these ReLUs, these rectified linear units, which are not exactly like real biological neurons, but they train much faster, right? And of course, ReLUs are used until this day. So you can see right here that this is on a CFAR10, and they measure the time to reach 25% of the training error. And this here is with the ReLUs, and this here is with the hyperbolic tangent. And it takes much longer to reach the hyperbolic tangent, especially it takes 6 times faster with the ReLUs. And they say that's one of the main components that allows them to learn this fast, to even experiment with these big networks, because their entire training time is 6 days, right? But they probably didn't train it only once. They experimented with it and saw what works. So if you have a couple of months of time and it takes you a week to train one of these things, you know, you can't afford a 6 times slowdown. Because that would mean you can only train like 2 models in the entire course of research. And that would severely hinder your progress. Now, we are at the point where that becomes true again with these giant transformer language models, where people can train it once. And then, you know, if they like GPT-3, they say, oh, we discovered a bug halfway through and we kind of fixed it, but we're not sure. We couldn't restart because it was too expensive. Yeah, maybe we're waiting for a moment. I'm still saying we're waiting for the ResNet moment in the transformers. But yeah, ReLUs, you know, here, not introduced here, but used here, and have been prevailing until today. Training on multiple GPUs, something, as I said, that didn't really get forward from here, especially the kind of GPU training. So if we train on multiple GPUs today, what we mean is that we have our model, right? And then we distribute that to multiple GPUs like this. And then we take a mini batch from the training data and we simply split it up, let each GPU do its thing on its subset of the mini batch. And then at the end, kind of calculate the loss and then backpropagate the gradients and synchronize the gradients between that. So we have one model that is on both GPUs. Here they distribute a model to two GPUs. And I'm also thinking that with frameworks like G-Shard, this could potentially have a revival right here, this kind of distributing your models, especially within the same layer across many GPUs, and then having cross communication only at some points. So their argument is this only has 3 gigabytes of memory, which limits the maximum size of networks can be trained on it. Turns out that 1.2 million training examples are enough to train networks which are too big to fit on one GPU. Therefore, we spread the net across 2 GPUs. Current GPUs are particularly well suited to cross-GPU parallelization, as they're able to read from and write to one another's memory directly without going through the host machine. Okay, so this means that here they say the parallelization scheme that we employ essentially puts half the kernels or neurons on each GPU with one additional trick. The GPUs communicate only in certain layers. That means that, for example, the kernels of layer 3 take input from all kernel maps in layer 2. However, the kernels in layer 4 take input only from the kernel maps in layer 3, which reside on the same GPU. So very, very interesting choice right here. And they justify this here, or they say the results. This scheme reduces our top 1, top 5 error rates by 1.7 and 1.2% respectively, as compared with a net with half as many kernels in each computational layer, in each convolutional layer on one GPU. The 2 GPU net takes slightly less time to train than the 1 GPU net. So first of all, I have to say big respect right here. Like I can imagine they did this, with the ReLUs and stuff, and they were already better than previous, because so just to go to the results, they beat the error rates of previous models by a ginormous amount. So this is what they knew right here. This is on the 2010 ImageNet split. So the previous best ones were like at around 28-25%, and here their best one is at 17% top 5 error rate. I'm going to imagine that they trained it first and were already better than the 25%. And I guess lots of people would just call it a day, would be like, oh, cool, we have this entirely new method. Not only did we show that we can train it, we actually showed that it's better, and bada boom, I have 0.1% better error rate, and everything else can be a separate paper. No, they stuck with it and they pushed it. Each of these things right here, they say, oh, this reduces the error rate by 1%. This reduces the error rate by 2%. And, really they went about it. How far can we push this with everything? I mean, just imagine you come and you train a network. I'm pretty sure they first trained on 1 GPU, right? And then they thought, maybe we can train an even bigger network by using 2 GPUs. And then they realized, well, it's going to take like a crap ton amount of dumb code to cross-synchronize and keep them in lockstep and blah, blah, blah. Like, it's not even easy to write multi-GPU code today with all the frameworks. Just imagine that. And for them to, having already observed that their network does better than everything that was previously, to sit down and do the cross GPU thing, experiment with, okay, when do we cross communicate and whatnot, that is very, very respectable right here. So maybe a lesson to be learned, or just the mentality of the people. Maybe they just had more time. They were like, okay, it's still like 2 months out, this competition deadline. I don't know, but this is not something that I see today very often. This kind of persistence and additional pushing and reporting of what works in these kinds of things. I mean, some papers do it, but most papers do it because only with all the tricks they can get that 0.1% improvement. And this one already had the improvement and did it anyway. Okay, but multi-GPU training didn't really, it's like splitting the models across GPUs, didn't really stick around, mainly because I guess the GPUs got larger in memory pretty quickly, so it wasn't that necessary. But also, I guess, because the frameworks were just too clunky, and now maybe with G-Shard, this is coming back. So worth another shot, I guess. Next one, local response normalization. This also didn't really stick around. It got kind of dumped in favor of things like batch normalization, but with the resurfacing of things like layer normalization, it comes back to this thing here again a little bit. So what they say is that what they want to do is they want to kind of normalize the response of these ReLUs. So what they do is each response, which is this alpha, or this A here, is normalized by the following quantity, and it's all the responses of the other neurons around them, or of the other kernels around them, and you can see the sum is over this weird quantity right here. So what does it mean? If they have a bunch of convolutional filters, and these are the activations, so these are the feature maps after the convolution, and yeah, so if I have like 10 convolutional filters in my layer, this is going to be the output. The way they normalize is they normalize each each output channel by averaging, you see here, dividing by the average response of the channels around them, right? So let's maybe say the 5 channels, so 2 channels in front of them and 2 channels behind them. This is going to be, they take the average across this one. And then for another channel right here, for this one, you would take the average of the 5 around that. This isn't really something that stuck around, I guess mainly because of the really dynamic situation right here. What people do today is they have things like layer normalization that simply averages across all of the channels, or they have group normalization that predefines these groups. Like there's 2 groups, and we only normalize within this group and within this group, so always the same. This kind of dynamic normalization across neighboring filters, as I said, didn't really stick around. Not really sure why, but I guess it was just easier to implement it otherwise, or it just worked better. Again, here they say this it was motivated well, right? This scheme bears some resemblance to the local contrast normalization scheme of that, but ours would be more correctly termed brightness normalization, since we do not subtract the mean activity. And they make it connection to biological neurons. Where is it? This sort of response normalization implements a form of lateral inhibition inspired by the type found in real neurons, creating competition for big activities amongst neuron outputs computed using different kernels. Okay, so kind of inspired by real neurons, but also kind of inspired by other people doing also some kind of normalization. So people already knew that normalization was helpful at some times, and this is what they employed right here. Again, reducing the top error rates by 1.4 and 1.2% respectively. So not a big improvement, but still an improvement. The last thing, overlapping pooling, again, a thing that didn't really stick around that much. Where they say, okay, instead of having a pooling layer, so if this is your image, and instead of pooling 2 by 2 in the stride of 2, like we do today, and pool it down to a smaller image, what we can do instead is we can pool with overlapping windows. So in that case, they pool with a 3 by 3 window, but they do always do stride of 2, so they have like these overlaps right here, resulting in the same size, but then each pixel right here has some sort of overlapping information from the pixels around it. Again, they say it reduces the top 1 and top 5 error rates by 0.4% and 0.3%. Maybe this didn't stick around because I'm not sure. Maybe because people found it doesn't work in other problems. Who knows? So the overall architecture, as we said, is described in this picture right here. So you have the input image, which you can see has 3 channels, and they use convolutional filters with a stride of 4 at the beginning to reduce the size. So at the beginning it's 224 by 224, and then it's 48 by, sorry, it's 55 by 55, that thing here, 55 by 55, 48 feature maps. You can already see, as we said before, the feature maps keep increasing, while the number of the dimension, the resolution of the image keeps decreasing. The stride of 4 convolution here already employed in order to downsample the image at the same time as convolving it. Nowadays, a lot of architectures will simply not do max pooling at all, but always use the kind of strided convolution to downsample image while convolving it. What you also see here is that they thought that the feature map size should also be large at the beginning and then decrease, which is a reasonable assumption, right? Because if you have higher resolution images, you're probably going to need higher resolution feature maps. This didn't really come through until today. As you know, most architectures today, they just go with like 3 by 3 kernels from the very start and don't really care about, you know, also downsizing their filters. I don't really know why, whether it's just more convenient or less parameters, or whether there's really something to having small filters. But I just know, you know, this is something, the large filters at the beginning is something that didn't hold over time. Also, you can see right here, they have multiple dense layers at the end. I believe most architectures today simply go with 2 of those instead of 3. So 1 like hidden layer and then 1 classification layer. But it's you know, it's very close to the architectures today, right? There hasn't changed that much. Like the difference between this and the VGG16, VGG19 network is just depth. And then the difference between those and the ResNet is just the skip connections right here. And that's where we are today. So there hasn't changed that much, honestly. They also allude to the fact that actually, even though it doesn't look like it, most parameters are here in these dense layers. Those are most parameters of the network. This right here, a convolutional layer, is like 1% of the parameters, even though it takes up a lot of space in the drawing. So maybe the reduction in the number of classification layers at the end also has something to do with the fact that that's where most parameters are. So if you get rid of one of those dense layers, you can get many more convolutional layers. All right, so the last part here is on reducing overfitting. Again, they didn't really investigate whether or not really their network was overfitting, like really establishing the overfitting. It was, I think maybe they did, and maybe it was actually overfitting. But we don't care about overfitting too much anymore. Maybe because we already use these augmentations naturally, but also because we built these deep models. So we somehow have an idea that they generalize naturally. I'm not sure whether they actually were only worried about it that much because of the history of machine learning, or whether they actually did see that everything was overfitting constantly. Okay, they say our neural network architecture has 60 million parameters. Although the 1,000 classes make each training example impose 10 bits of constraints on the mapping from image to label, this turns out to be insufficient to learn many parameters without considerable overfitting. Below, we describe 2 primary ways in which we combat overfitting. Again, no one today makes this argument anymore. We have this many parameters and there are that many images, right? We have 60 million parameters. We have 1.2 million images, 1,000 classes. How many parameters per sample is that, and so on? How many bits of constraint? We don't care about that anymore. We're fine with having like 1 billion times more parameters than training samples. We don't worry about it anymore. So the first thing they do is data augmentation. Already, this was already known again. Like lots of these things here were already known, but the combination is just so cool in this paper. So first of all, again, they say the transformed images are generated in Python code on the CPU, while the GPU is training on the previous batch of images. So these data augmentation schemes are in effect computationally free. Again, this code must have been ugly. The first form of data augmentation consists of generating image translations and horizontal reflections. We do this by extracting random 224 by 224 patches and their horizontal reflections from the 256 by 256 images. Okay, so this was already, these are the most valuable data augmentations that still we have today. Random horizontal flipping is still used in every pipeline of computer vision, except if you want to read text, I guess. And random cropping is still the most powerful data augmentation technique for images today. And it's crazy that this was already discovered, and I don't know whether they say right here how much this particular thing improves. I don't think they have a stat on how much this improves. They just say how much this next thing improves. But I'm going to guess this was one of the vital things for pushing the performance, because now we know cropping is very important. I guess they thought that they would, translation was the important part. And so they focused on generating image translations. And to generate an image translation from a single image, naturally you have to crop it. However, we now focus much more on the fact that we crop it and kind of have different sub-images of the same image, especially in self-supervised learning and things like this. We know that cropping is like the power horse of these methods. So the fact that they extract random patches right here means that their network only operates on these sub-patches, and then they compensate by, at test time, the network makes a prediction by extracting 5 patches, the 4 corner patches and the center patch, as well as their horizontal reflections, and averaging the prediction made by the network's softmax layer on the 10 patches. I also believe that people don't do this too much nowadays. They most of the time they simply rescale the test images or something like this, or fine-tune at the end on the kind of scale training images. There are various techniques for doing this, but random cropping and horizontal flipping already employed right here. Also, color jittering, a form of color jittering, a very special form. Altering the intensities of RGB channels in training images. Specifically, we perform PCA on the set of RGB pixel values throughout the ImageNet training set. To each training image, we add multiples of the found principal components with magnitudes proportional to the corresponding eigenvalues times a random variable drawn from a Gaussian with 0 mean and standard deviation 0.1. This is, I believe, this has gone out of fashion. So people do color jitter and kind of brightness jitter and so on. But I don't think they particularly do this kind of PCA-based image augmentation right here anymore. They say this scheme reduces the top 1 error rate by over 1%. I wonder why this isn't working. Maybe because you need these stats over the entire data set, and the other things may be working equivalently well, but you can simply apply them without knowing kind of your principal components. Okay, next thing, dropout. Dropout has been, one of the things that was very important throughout the early stages of deep learning isn't that important anymore now. Dropout, some people still use it, but most people, I think, don't use dropout anymore. And it's very interesting to see, but it definitely was a technique that was used a lot during, from AlexNet to basically now, the last very few years. So they say, combining the predictions of many different models is a very successful way to reduce test errors, but it appears to be too expensive for big neural networks that already take several days to train. There is, however, a very efficient version of model combination that only costs about a factor of 2 during training. So there's this technique called dropout, and they explain it to set to 0 the output of each hidden neuron with probability 0.5. Again, people didn't know about dropout as they do now, but they introduced this right here, and they say it reduces their, not sure, yeah, they also don't say how they, how much this reduces the training error, but they say we use dropout in the first 2 fully connected layers. Without dropout, our network exhibits substantial overfitting. Dropout roughly doubles the number of iterations required to converge. So, okay, so they did actually make sure, or they did find the actual evidence of overfitting and saw that dropout reduces that. And I wonder why this doesn't happen nowadays. Maybe because we have less of these fully connected layers, but I can't really imagine. Maybe because we do more augmentation. I don't know, or maybe dropout is still used and I just don't know it and don't see it. Yeah, so here they use momentum to train this, and they do some qualitative analysis. They do some qualitative analysis. So first of all, they say, okay, they shatter all of the previous approaches, especially also then they build kind of ensemble methods, and they pre-train. They already do transfer learning. They already pre-train on ImageNet 2011 and fine-tune then on the ImageNet 2012, right here, the ImageNet 2011, and then fine-tuning on the ImageNet 2012 to reduce that error even further, like pulling all the tricks. All of these things are around still. Very cool. And then they look into what their network learned. So they find that there are a number of these kind of filters. You see these 11 by 11 filters in the first layer where they show, okay, this really, and this was kind of already known, that these neural networks extract filters like this, like color gradients or edge detectors in various forms and directions. And cool to see that this one also does so. This one here is also a very cool investigation where they look at examples, and the red bar, the red one, is always the correct label, and the bars are basically what their model says are the top 5 things. And it's cool to look at. So for example, here you have mite as the top one, but then also black widow, cockroach, tick, and starfish. But the top labels are usually also very, very good labels. You can see here grill, and it assigns convertible, which, you know, by all means is correct. It's just not the class that the annotators assigned to this particular image. As well as here, Dalmatian was the highest prediction of the network, where the label was actually cherry. And yeah, this is quite debatable, right? So you can see that a lot of the mistakes the network does are forgivable, let's say. And you can see that for when the network doesn't do mistakes, not only the top label is good, but a lot of the top 5 labels are also very, very adequate. Lastly, they look at a given training set image, which these are the training set images right here, and they look at the last layer's feature vector and the 5 nearest, or the nearest neighbors in Euclidean space of the entire training data set. And here's what you come up with. So you can see for the elephant, the nearest neighbors are all other elephants. And regard that they are in different poses, right? They don't always look the same way, these elephants. Also, these dogs right here. So it's pretty cool to see that the network actually learns some invariances across the class and puts images with the same label into the same area in the embedding space. Yeah, so that's their paper. They already allude to the fact that depth is very important. It is notable that our network's performance degrades if a single convolutional layer is removed. For example, removing any of the middle layers results in a loss of about 2% for the top 1 performance of the network. So the depth really is important for achieving our results. And as you know, this spurred an area of trying to build deeper and deeper networks until ResNets came along and built ultra deep networks. They also say we did not use any unsupervised pre-training, even though we expect that it will help, especially if we obtain enough computational power to significantly increase the size of the network without obtaining a corresponding increase of the amount of labeled data. Thus far, our results have improved as we have made our network larger and trained it longer, but we still have many orders of magnitude to go in order to match the inferotemporal pathway of the human visual system. Ultimately, we would like to use very large and deep convolutional nets on video sequences where the temporal structure provides very helpful information that is missing or far less obvious in static images. So already the previewing of future research here with the self-supervised, with the many more layers and so on, astounding that this kind of foresight, and of course all of this proved to be very, very adequate predictions right here. And yeah, so this was the paper right here, the paper that kicked off deep learning. I enjoy reading kind of these old papers, especially looking back at what was already known, what still is around, which turns out to be a lot. A lot is still around. And the choices that people made back then, some of them defined our modern field. So that was it for AlexNet. Let me know what you think in the comments, and I'll see you next time. Bye.